Today we are going to discuss Chapter 12, Confidence Intervals and Test for the Slope of a Least Squares Regression Line.
I'm going to talk about the state plan to conclude for confidence intervals and significance tests. So typically for a confidence interval, we would say we want to take a blank percent confidence interval for the slope of the regression line. For a significance test, we would say the null hypothesis, the slope equals 0, and the alternative hypothesis, the slope does not equal 0, where B is the slope of the least squares regression line, and state at the significance level you're testing at. Plan for both confidence intervals and significance tests, they both follow the same steps. Linear, independent, normal equals standard deviation and random. To check if it's linear, you must look at a residual plot, and if there's no curve pattern, it is linear. To check if it's independent, you must check the 10% condition. To check if it's normal, you must check the distributions of residuals for normality at each possible x value. To check if it has equal standard deviation, you must look at the scatter of residuals above and below the residual line at 0. The spread should be roughly the same. And to see if it's random, it must be a random sample or a randomized experiment. So the do step for confidence interval and significance test. So for confidence interval, it is slope plus or minus the t-critical value times the standard error of the slope. The degrees of freedom is n minus 2. For significance test, it is t equals the slope minus the null hypothesis over the standard error of the slope.
A common mistake for performing a significance test is forgetting to multiply your p-value by 2 during a two-tailed test. You would notice a two-tailed test when the alternative hypothesis, the beta value, is not equal to the hypothesized value as shown in the pictures below.
Conclusion, confidence interval, we would say that we are blank confident that the true slope for least squares regression line is captured in the interval blank to blank. For significance test, if the p-value is less than a, we reject the null hypothesis and we would say we have convincing evidence that the slope of the least squares regression line is non-zero. And if the p-value is greater than a, we fail to reject the null hypothesis and we do not have convincing evidence that the slope is not zero.
In a computer output, there are several key variables: A, the y-intercept; B, the slope; SEB, the standard error of the slope; S, the standard deviation; and R squared, the coefficient of determination. A common mistake is mixing up R squared adjusted with R squared. They are not the same thing, so when asking for the coefficient of determination, you should just put the R squared. Using the information from above, we now have enough info to write the least squares regression line.
Standard error of slope describes if we were to take many different random samples of n and compute the least squares regression line for each sample. The estimated slope will typically vary from the slope of the population regression line for predicting slope by about the standard error of the slope. Standard deviation is how far you typically are off from the least squares regression line. When using the least squares regression line with x and y, we will typically be off by about the standard deviation.
There are two types of transformation for linearizing data: the power model and the exponential model. In the problem below, the original scatter plot is not linear. We perform two transformations, the exponential and the power model. We know that the graph 1 is the power model because there are two natural logs on both sides of the equation. And the second graph is the exponential model because there is only one natural log on one side of the equation. We can tell that the power model is a better model for linearizing the data because the residual plot is a random scatter and the scatter plot is roughly linear.
This is our sample AP problem. John believes that as he increases his walking speed, his pulse rate will increase. He wants to model this relationship. John records his pulse rate in beats per minute while walking at each of 7 different speeds in miles per hour. A scatter plot and regression output are shown below.
For part A of the AP problem, you're going to use the computer output to create the least squares regression line and define your variables. So y hat is the predicted pulse rate in beats per minute, and x is John's speed in miles per hour. For part B of the problem, is asking you to define the slope and the y-intercept. So for the slope, you would say for every 1 additional increase in miles per hour to John's speed, there is a 16.2809 increase to the predicted pulse rate in beats per minute. And for the y-intercept, you would say for 0 miles per hour in John's speed, he has a predicted pulse of 63.47 beats per minute, and you need to state that this makes sense because 63.47 is a pulse, which means that makes sense. For part C of the AP problem, we're trying to find the margin of error John should use for his report. So conditions, they said, were satisfied, so we don't need to do liner. So we're going to use the margin of error formula, which we've written out for you below. And for that, we need to find the t-critical value, which means we need to find the degrees of freedom. So we're going to do n minus 2. And we can find n by looking at the plot that they gave above, and there's 7 dots, which means that there's 7 samples. 7 minus 2 is 5 degrees of freedom. And then we're going to use the fact that they told us it was 98% confidence interval to go into the table and find that the t critical value is 3.365. And then the standard error, the slope, is given in the computer output, and we'll plug that into the formula and then write the conclusion. For 98% confidence interval, John should use the margin of error 2.7866.